temperatures of the moon. So take it away.
Thank you. Great, thank you. So I'm going to talk about global surface temperatures of the moon as seen through the eyes of diviner. My purpose of this talk is really to kind of give everyone a preview of some new data products that myself and the diviner team are putting together and we'll hopefully have available in the coming months. Now that our data density is getting fairly high, we can start to make some nice products for the community. Let me give a brief overview of Diviner, since I think this is the first Diviner talk of the meeting. But Diviner has been gathering reflected solar and emitted infrared radiation measurements for 5 years now in 9 spectral channels. And I'm going to talk about the bolometric brightness temperature, which we derive from the 7 infrared channels that span from about 8 microns to about 400 microns. And now that we've got enough data, our density of data is getting high enough that we can start to look at the diurnal temperatures globally all over the moon. And we're starting to be able to resolve basically the diurnal temperature curve everywhere. And so we can make some nice global maps of surface temperatures. So the nature of LRO's orbit is that the subspacecraft longitude cycles between 180 and a negative 180 degrees longitude every approximately 27 days. So every lunar day we get full global coverage. And what I've done is, and so every lunar day we can basically make a temperature map of the moon, but I've put together 7 of these maps, and you can see that the temperatures actually drift throughout each of these maps. So we're getting different local times with every map cycle. And so the local time is drifting by about 2 hours with each map. And eventually across the terminator, and then the day side, night side nodes of the orbits flip. So we're getting basically 2 local time measurements with every orbit. And then the subspacecraft local time cycles between 0 and 24 hours once every year. So every 6 months we basically get local time coverage somewhere on the planet at all local times. Now if we zoom in into one of these maps at the full resolution, you can see that our orbits, these are the daytime are the hot reds and the nighttime are the blue. Our native sort of resolution in our nominal mapping orbit of 50 kilometers is about 128 pixels per degree. But you can see that's just in these orbital tracks, and then you've got large gaps. You've got areas where we're doing a lot of calibration things with the instrument where we're looking away from the surface. And you could see even in these low-res maps that there are gores in our data where, for whatever reason, we're not taking data. So it's taken a long time to build up enough data at all local times everywhere to really start to put some of these maps together. And I think we'll still need a lot more data before we can really start to make some maps at this resolution. But for now, what I'm doing is creating maps at half a degree resolution. And what I've done is taken the entire data set to date and binned it at half a degree resolution, but also binned the local time and essentially build up a diurnal temperature curve for every map pixel. And so once we do that, you can then pick any subsolar point you want, and then based on the relative local time of each map pixel, interpolate what the brightness temperature is at that pixel. So you can build up these snapshots of the lunar temperature. And so here the subsolar point would be at plus or minus 180 degrees longitude. And so here's some examples of each map pixel has a temperature curve associated with it. And so you can kind of see, especially around the dawn terminator, it's a very complex signal. There's also a little bit of some artifacts that kind of show up, some vertical striping, and this is an issue that shows up where we do have some gaps in our local time coverage, especially where you've got this large change in temperature around the terminator. You've got this inflection, and if you're not resolving that very well, for example, over here, you're going to not have a very good interpolation there. And so as we take more and more data, we start to fill in these diurnal curves everywhere. Well, this map will just keep getting sharper and sharper. And so the idea is we'll start, you just kind of keep releasing these and updating them. And hopefully, as we get better local time coverage, we can start to actually increase the map resolution as well. So it's sort of a trade-off. And then what we can do then is use different parts of these diurnal curves to do science. We use the nighttime temperatures and how the lunar regolith cools at night and how it radiates away that sensible heat that it's stored up during the day. It tells us a lot about the thermophysical properties of the regolith. And around the terminator, where we've got low sun angles, that tells us a lot about the surface roughness of the moon. And then we used the noontime temperatures we use for getting at some of the compositional information. So the idea is to keep building up these maps, and they're going to get better and better as Diviner continues. And so it's actually really important that we really resolve that the local time right around the terminator, because that's, of course, where those gaps in the local time really show up in our maps, and it looks kind of messy. But this gives you an idea of how that coverage is improved with time. So these are the different mission phases, and right around the the dawn terminator. So this is the ESMD, SMD, and our extended mission. And so at this resolution, we're sort of at about 55% coverage of the terminator right there. But again, this will just keep improving as we keep running the mission. I originally made these maps as part of the Science on the Sphere outreach project, and that was back in March 2012. And so you could see that these artifacts are actually were much worse, and now you can kind of see how that's improved with time. So hopefully we can just keep running Diviner as long as we can and start really improving these maps considerably. The other thing we can look at is, here I've created an average temperature of map in the top half, where I've basically taken longitudinally averaged the diurnal curve and basically gone through the same process of creating these maps. And so you can kind of see in an average sense what the lunar surface temperatures are when the subsolar point is at 0 longitude. And then here you can really see how the topography really drives the temperatures at low sun angles. So anyway, so I just made some figures here where you can kind of move the subsolar point around and actually look at the entire, every phase of the moon in its diurnal cycle. Of course, you can't click through this quickly enough to make it kind of a nice animation, but anyways, yeah, this is really slow. Get through this. All right, come on. Okay, so one of the things we can also pull out of these maps is, for example, the maximum global temperatures, which don't really show up very well on the screen at all. They actually show up better on those monitors, but again, it's largely a function of latitude, but you can see how albedo towards the equator really can cause the noontime temperatures to vary. We can also pull out minimum lunar temperatures shown here, and what really shows up here quite nicely are the rocky areas. So all these bright regions here are one of these Copernican-aged impact craters, where you have a lot of coherent blocks that have been excavated, and they stay nice and warm during the lunar night because they have a higher thermal inertia. They form sizable reservoirs of heat that they've absorbed during the solar day. And Giordano Bruno is actually probably the hottest place in the lunar night. It's a very fresh, young crater. Yeah, it's just to give everyone a frame of reference. So the other thing you could do is pull out different hours of local time during the evening and watch how the whole surface of the moon globally cools throughout the night. And so we can sort of step through it and see how the temperatures change. So one of the other things to make it a little more obvious what the sort of thermal anomalies are during the night is I took the nighttime bolometric temperature maps and then differenced them with that averaged temperature map, creating an average nighttime map. And if you difference that, then a lot of the thermal anomalies in the nighttime maps really come out, become much more obvious. And again, it looks terrible up here, but it looks better over there. And again, you can see a lot of these impact basins. There's Tycho, there's Giordano Bruno. You can even make out some of the rays coming out of Giordano Bruno. Imbrium, Procalarum show up. And there's actually some very interesting features, these anomalously cold spots. This is something that was identified by Diviner. These are very fresh impacts that have these anomalously low regolith temperatures associated with them. And this is something Josh Banfield has a couple papers out on. So these are kind of interesting features. So anyways, yeah, as we start to get these maps, sort of the data density continues to improve, a lot of these maps will get sharper. We're in the process of recalibrating a lot of the level 1 data too, which will also help improve some of the maps here, and hopefully in a couple of months we'll start putting these online and getting them published. So what we're doing is systematically mapping the thermal state of the moon, and so we're getting a better constraint on the diurnal variations of the temperatures globally. So most of our results so far, we've had to do a lot of averaging to get at the thermal physical properties, for example. But now we can start really creating some nice maps. And this will really help us characterize the surface energy balance of that regolith and how that regolith is really exchanging heat as a result of solar forcing. We really find that the lunar regolith is really a very extreme thermal environment. It doesn't have much of an atmosphere. It's to buffer surface temperatures. It's a very highly insulating surface. It's got a very low thermal inertia. So you get these extreme thermal gradients, and down to length scales as small as we can see. And some of our modeling shows that you can have 100 Kelvin gradients that are just centimeters apart. And so, and then at the terminators, again, you have a very complex temperature field just due to the topography at low sun angles. So at high latitudes near the terminator, temperatures are very complex. Yeah, nighttime temperatures are really indicative of the thermophysical properties as we see the surface cool and the heat from deeper and deeper levels in the regolith start to radiate out later in the evening. It gives us an idea of the vertical profile of the thermophysical properties. And so now we can really start looking at variations across the surface of the moon. And with that, I'll just put up my email. If anyone would like to have some of this data and they don't want to wait for it to come out in a few months, they want some preliminary versions, just go ahead and email me. I'm happy to let people have versions of it. Yeah.
Thank you. Okay, we have time for questions. Carly, do we have? Oh, wait for the microphones. We have the Adobe Connect people out there. Okay.
Okay. Boop, boop. Okay. Carly Taylor, Brown University. Really interesting stuff. With the current coverage that you have, can you put general range of the resolution that you can do these thermophysical properties of? Because clearly that's a function of what your coverage is. What would be your estimation that is right now?
I think it kind of depends on what you're trying to do. In this case, with these maps, it seemed like half a degree was good enough to get enough resolution in the local time. It's sort of a trade-off. As you increase the spatial resolution, you lose your local time resolution. If you're creating maps where you're averaging a lot of these map cycles together, you're not so worried about that. We've been able to do some bolometric temperature maps, all the way up to 128 pixels per degree. But again, because you're dealing with time varying all the time, you can do individual map cycles at different local times. But if you want one spot and you want to really resolve that diurnal curve, you got to be careful can't go too high in your resolution. But again, as the more data we collect, the better we can make these.
Can I have a second question?
Of course you can have a second question. Go ahead.
I realize doing latitudinal issues are very complicated because that's temperature variations as well. But in terms of the thermal physical properties, do you see any latitudinal variations? Not necessarily at the poles, because that's probably really difficult, but at least as a function of latitude, any thermal physical variations that you've currently seen?
Paul, are you going to get into? Yeah. This gets a bit into Paul's talk, which is next, where he's going to talk on that very subject. So maybe we'll be pulled off and let Paul.
Okay. Any other quick questions? Okay, thank you very much.